Today we study RC circuit. The RC circuit consists of EMF, resistor, and capacitor. EMF is simply battery or any power supply. Today we consider a direct current only. So the battery is enough to explain any source of EMF. The potential difference between the two terminals A and B, this negative terminal and positive terminal, is E. If a small amount of charge passes through this battery, it gains the energy, electrostatic energy, like that. Because this potential difference is E, so we have E dq is the work done by the battery, and positive electric charge accept the potential. Another circuit element consisting of the RC circuit is a resistor. And resistor, we have symbol R that represents the resistance of the resistor. If the current I flows along this direction, due to the resistance, electric charge, positive electric charge that passes through the resistor loses its potential, and the amount is resistance multiplied by current. So delta V along the direction of current is minus Ri. You should be careful with allocating the sign. Resistor consumes energy with the power Vi, and because V is Ri, the amount of power spent by the resistor is Ri squared. This is positive, and this is energy loss per unit time happening inside the resistor carrying the current I. The third part is the capacitor. Capacitor is charged with positive and negative charges. The amount of charge, the magnitude of the charges are the same. From the positive to the negative, the potential decreases, and the amount of change in potential is Q over C. Because this is a positive and negative, the potential on the negative plate is always lower than the potential at the positive plate. Therefore, if you pass through the capacitor from the positive terminal to the negative terminal, you will lose the potential by Q over C. Again, you need to be careful to allocate the sign. The capacitor saves the electrostatic energy. We learned already the amount of electrostatic energy is 1/2 CV squared, and because Q equals C times V, it is equivalent to Q squared over 2C. When we compute the kinetic energy, sometimes we write it in terms of 1/2 mv squared, and because mv is the linear momentum, it can also be written in the form p squared over 2m. Just like that, we can either write 1/2 CV squared or Q squared over 2C. Analyzing a current with energy. Battery supplies energy. Resistor loses energy. If current I flows, amount of charge dq passes through any point during the time interval dt. That is I. So power supply equals EI. During the time, the energy supplied is multiplied by power. Power loss is RI. RI is the potential, and you need to multiply I to compute the power. This is RI squared. And if we multiply dt, that is the amount of energy. Energy supply, energy loss. Energy supply and energy loss. Okay? If I cancel I dt, what I get is E equals IR. Analyzing a circuit with potential. Potential, let us assume the potential at point A is VA. Let us follow this direction along the current I. This is a negative and positive terminal. At here, in the beginning, it used to be VA. If you pass through the terminal of a battery from negative to positive side, you will gain the potential. The gain of potential is plus E. Okay, all the way along, this we still the same, because along the wire we assume the resistance is 0. Let us pass through this resistor. There is a potential difference by IR, but along the direction of current, you lose the potential. So here V plus E, but here you will get V plus E minus IR. So this is this. When you return to the same point, if there is no magnetic field that is depending on time, so in electrostatic case, you will find that the potential difference should be 0. So the potential at this point in a steady state must be the same every time. Therefore, you will return to the same point. This is called the Kirihope's loop rule. In here, you cancel this VA. This does not contribute to any physics. So E equals IR. You get the same result if you make use of potential or if you make use of energy. In either way, you will find the same rule for the resistor's potential difference. Why don't we connect the resistors in series? Here we have N resistors, and each of them has the different values for the resistance. If you follow this direction, and make use of the Kirihope's loop rule. If you follow this direction, you in the beginning it used to be VB and minus R IR1 and so on, minus IRK and so on, minus IRN. And you pass through this battery from minus to plus. So it is E equals 0. No, VB plus VB and VB cancels. This one shows that I times sum of R's equals E. So we call this sum of R to be equivalent resistance. Equivalent resistance. If resistors are connected in series, then the equivalent resistance is just the sum of every resistor. Potential difference at difference between the two terminals of every resistor can be computed once you determine the current. Current is completely determined by E over sum of R's. Substitute in here to every equation V1 equals IR1, V2 equals IR2, and so Vn equals IRn. Everywhere, current is invariant. There is no change in current. What about the case of parallel connection? If you have resistors connected in parallel, the current I is divided into many pieces. I comes in and I1 through IN. Because of the electric charge is conserved for a certain time interval delta t, the amount of charge enter into this node must be the same as the amount of charge leaving out of the node. So this one should be the sum of all of the currents. So in the case of a parallel connection, sum of current should be the same as the current passing through the battery. In the meantime, we are looking for a single resistor that has the equivalent system. So I and R and this II the same. So what should I do? First of all, our strong constraint is sum of currents. And each current, I substitute E over R because this is E and this is E. In here, every potential difference must be the same as E. Haha, that's the reason why I have substituted this one. And in here, E over R K. And EE cancels. What we find is the reciprocal of the equivalent resistance R. Let's consider a case if there are loops. For example, this kind of parallel connection produces loops. As a simplest case, the simplest case, we have two batteries in opposite direction, and we have three resistors. They are all connected. We learn some terminology. Branch, these are all branches, circuit elements. Circuit, I don't say this wire that simply connects two terminals of circuit element. Any circuit element is called branch. Junction, or node. Here we call junction. We don't say this is a junction because it is just equivalent to the straight wire. So this is not a junction, but this is a junction. Current is divided into more than two pieces. Right. Equal or more than two pieces. Here, there is no division of current. So it is not a junction. Junction rule, current conservation. Incoming current is the same as outgoing current. Or in some cases, let every current directed to a single point. Then in that case, sum of all currents must be zero. This is junction rule. Junction or node. Loop. This is loop. Loop is any closed path in a circuit. How many loops are there? Yes, this is a loop, this is a loop, and this is another loop. Loop rule. In a steady state, potential at every point is independent of time. Therefore, in that case, when you return following a loop, when you return the same place, you will get the same potential. This is a loop rule. You have three loops. However, these three loops are not all independent. You don't have to worry too much about it. Instead, the simple question is, if you have circuit elements, they are called branch. The number of branches, you are interested in determining the potential. Once you know the potential, then you can determine the current, something like that. Here we have 5 branches. However, the answer is known for these 2 batteries. So we don't have to worry about these 2 branches that are already fixed. I'd like to know the potential, either potential or current at each branch. That's our question. We have 3 unknowns. 3 unknowns. And we need 3 linear equations to solve this problem. That's the situation. We have junctions. Junction mean where I can use the current conservation. Not every junction is independent. Just subtract single one from the total number of junctions. So I have in here, independent junctions is 2. So J minus 1 is 1. Only a single relation I can use for the current conservation. Because I have three unknowns, and one equation, what I need to do is I need to find two more equations that comes from loop rule. This loop, this loop. If you add one more loop, you will find a redundant equation that is not necessary anymore. You could include redundant equation, but answer will be the same. So, even though there are 5 branches, because 2 potentials were known already, we have 3 branches. Branch means 3 circuit units whose potential and current must be known. We have two junctions, so J minus 1, only a single independent junction rule that is nothing but the current conservation. There are 2 independent loop rules. Without this, we cannot solve this problem. That we can choose either this. Among there are 3 loops. Choose any 2 of the loops and write down the potential. For example, start here, B to here, you have increased the E1. Follow this line, you have decreased the potential by minus IR1, and then this is this loop. Okay? Because you are following this direction, potential has increased. I have allocated I1, I3, I1, I3, I2 along this direction. In the case of this loop is opposite to this current E3, so that's the reason why we have positive sign on it. Small loop, right small loop. Let's choose this direction. Here, follow this line, minus I3, R3. Follow this line, I2, R2, minus. And follow this direction. It's opposite to the direction from the negative to positive terminal, all negative. We can solve this linear equation, and inverse can be obtained easily. A, B, C, D. Multiply the inverse both sides, you will find the final result. Remaining piece in here, we first determine E2 and E3, and sum of E2 and E3 will determine I1, I2, and I3 will determine I1. So we will find sum of these two is this. Sum of these two is this because of this relation. Next, we consider RC circuit. RC circuit consists of a battery and capacitor. In addition, there is a resistor. Charging process. Q equals 0. In here, at t equals 0. And suddenly, you close the switch to here. Then, current flows along this direction, and positive charge, is being accumulated on this plate. However, if you have a charge Q, you will find that the potential difference between the two plates will be Q over C. And when it reaches the same potential, then the amount of this force, electrocoulomb force to push the positive charge, actually negative charge is moving backward, but let us consider positive charge. This force and this force, their positive charges are being accumulated. They make an equilibrium. So there is no way to allow more charge to the right because they fight each other and they make an equilibrium. So usually it is difficult to charge more charges as a capacitor is being charged. So initial state it is easy to charge a capacitor, but as time goes by, it is difficult. Anyway, we have a certain constraint that capacitor stops being charged. And then if it is completely charged, then what about the case? Let's consider switch. This is both E, equilibrium. And in that case, just switch to B. In that case, this battery is lost. However, this positive charge will flow backward, and this one behaves like a battery. Okay, so empty one, discharged. Charged one, charged. After a capacitor is completely charged, it can behave like a battery. That's a mechanism of an RC circuit. Charging of an RC circuit satisfies this kind of equation. And this is a first order linear differential equation. And it is completely solvable by separation of variables, as we have done with the falling body on the drag force. Here, the solution is this. Why? First of all, particular solution, simple solution, constant value solution is just ignore time dependence. If you substitute the constant C, constant alpha, then RC equals E over R, cancel. So alpha equals CE. So this term is the particular solution. Once you know the particular solution, then you are better to add up a general solution for the corresponding homogeneous equation. If there is no battery, you can solve this equation. This is dq over dt q minus rc, okay? Q over dq rc dt. What's that? Log q over q t0 equals e to the minus rc t. So q equals q0 e to the rct, something like that. In this case, there is a free parameter because if something is a solution, then any solution multiplied by a constant parameter is also solution. So linear combination. So this parameter should be determined by making use of the initial conditions. If Q0 is 0, then we substitute t equals 0 to find that alpha is minus 1. If I take the time derivative, I can obtain the current. In the charging process, the current Due to the shape of this exponential function, it approaches the maximum value, that is a CE. You know, the current flows a lot at the initial stage, but the current vanishes as the t goes to infinity. So why don't we compute the electrostatic energy saved in the capacitor? We can make use of charge Q at time t. Substitute this one to the electrostatic energy, 1 half CV squared, to obtain the result. Again, as time goes by, this one vanishes. This is the amount of electrostatic energy that is being saved inside the capacitor. In the meantime, we can compute the energy loss due to the resistor using this current. The value is this. So, battery supplies energy and part of it is being saved inside the capacitor, but there is no way to prohibit this loss of energy. One cannot avoid this loss. You must know that exponential has an argument that is dimensionless. This RC is simply a constant. When R is 1 ohm and C is 1 farad, that time is just 1 second. We say this RC, that is of dimensions of time, the capacitive time constant tau. And once tau is known, numerical value for the Euler's number E is quite important to determine the shape or transition of charge or current as time goes by in units of time constant. So you need to remember numerical values for these approximate. You don't have to remember everything, but just remember at least the 2 digits. Discharging. When the battery is disconnected and capacitor is being used as a battery, then capacitor becomes the source, so it loses its charge. Again, charge flows in opposite direction in comparison with the case of charging process. Again, as time goes by, the charge decreases and current decreases too. The solutions are trivial. So, using the same method, you will find the initial current is this, and potential difference between the 2 terminals of resistor decays exponentially. Again, the potential difference between the 2 places of capacitor decays with the same rate. That's it.